Hello, my name is Anabel Renteria, and I'm a PhD student in the Mechanical Department under Dr. Gino Lin's supervision. The title for my project is Lattice Design's Influence on Mechanical Strength for Piezoelectric Sensors Fabricated Using Freeform Extrusion 3D Printing Technique. The outline includes the motivation behind this project. Then I'll introduce a little bit of background. After that, I'll discuss the project objective, followed by the material properties. Then I'll talk about the geometry, followed by boundary conditions, then mesh optimization, finally results from the simulations and discussion, and final conclusions of this project. The motivation for this project is to use 3D printing technology to fabricate functional devices with a high degree of customization and the possibility to evaluate different materials with similar mechanical properties for different applications. First, I would like to introduce the concept of piezoelectricity, which refers to the materials that generate an electrical signal when a mechanical loads are applied. Piezoelectric materials, especially piezoelectric ceramics, are an area of interest due to their good piezoelectric coefficient compared with piezoelectric polymers. The most used piezoelectric ceramics are lead zirconia titan, also known as PCT, due to its high piezoelectric coefficients or 450 picocoulombs per Newton in average. However, due to their lead oxide content, researchers has up to evaluate lead-free piezoelectric ceramics, and one of the most popular is barium titan, also known as BTO, which has a theoretical piezoelectric coefficient of 191 picocoulombs per Newton. So a lot of research focus on the optimization of this piezoelectric coefficient, reaching values closer to PCT properties, which make it a competitive alternative option compared to PCT. Some of the materials properties of ceramics are that they are brittle due to its manufacturing complexity, and they are very likely to deform and generate cracks. In the case of piezoelectric ceramics, they are under compression in order to generate an electrical signal. Therefore, it is important to analyze the mechanical strengths and the deformation of ceramics under loads. 3D printing consists of the deposition of material in a layer-by-layer fashion. There are several 3D printing techniques. Among all of them, paste extrusion is a 3D printing technique which is popular because you can fabricate high-density ceramics with material properties close to theoretical values. Literature indicates that computer simulation has been used before to analyze cracks propagations in ceramics. In this case, we have a multi-layer capacitor in which they use BTO as piezoelectric materials. They do a 2D analysis and they evaluate the cracks by inducing such cracks in the mesh before running the simulation. The objective for this project is to evaluate the lattice structure design for two different piezoelectric ceramics, which have the purpose to be used on energy harvesting devices. This lattice structure will be under compression, and the deformation, total stress, and strain will be the output indicators to select the most appropriate material. Piezoelectric ceramics behave as anisotropic materials, and literature suggests that the following values must be used for BTO and PCT. For this simulation, a 2D design will be evaluated. The geometry considers the use of a nozzle of 1.5 millimeters and a space between rows of 1.5 millimeters too. And that's how the design of the geometry came from. I create this geometry using the tool surface from sketches. The boundary conditions were as follows in the pictures. As you can see, a fixed support was applied on the border of the lattice, while the force was applied all over the surface. Different mesh were evaluated using adaptive sizing with different resolution values and also fine angle curvature. As it can be seen, the more resolution increment the number of nodes, and also this helps to reach convergence in the results. From the simulation, it can be seen that the BTO generates a total deformation of 0.05, while the PCT structure forms a total deformation of 0.02. And for both materials, the deformation affects more in the middle of the lattice structure. In another hand, the equivalent stress for the BTO is the double value compared to the PCT structure. Finally, the strain for BTO is also bigger than the PCT. This means that the BTO will deform or elongate more compared with PCT when a force is applied to the structure. As a conclusion, a 2D simulation model for a lattice structure considering two different materials was evaluated. A test under compression was performed and a total deformation, equivalent stress, and strain were obtained. The PCT shows a better response to mechanical loads without deforming, meaning that it is less likely to develop cracks compared to BTO. In terms of crack generations, PCT should be selected for this specific design. That's it for my part. Thank you so much for your time.